Hello everyone. In this video we are going to be talking about which functions are also eigenfunctions of different operators. And in these two exercises to be done together, we have operator first derivative and operator second derivative. So to remind ourselves of the eigenvalue equation, we have operator times wave function should yield eigenvalue times wave function. So when we perform this operation on the function, basically we should get the exact same function back plus a constant in front of it. So for number 10, which we can do first, since it's the first derivative, operator equals d over dx, we can start with the first function, e to the ikx. So taking the first derivative, for exponents, you just pull out what's in the top, and this is what we get. So we have the same function given back, e to the ikx, plus a constant, I times k. So here, yes, this is an eigenfunction of the first derivative operator, where the eigenvalue is ik. For the next, cosine kx, we get negative k sine kx. So here, we don't have the same wave function, even though we do have a constant in front of it. So this is not an eigenfunction of this operator. Next, we have kx, where the derivative of kx is just k. So here, we don't even have a function to follow the constant that we get out. So again, not an eigenfunction of this operator. And finally, we have e to the minus ax squared, where we get minus 2ax e to the minus ax squared. While here we do get the same psi back, we don't actually get a constant back. Here, minus 2a is a constant, but this x is a variable, which means that this can change. So even though we get the same function back, what's in front of it isn't a constant. So this function is not an eigenfunction of the first derivative operator. So now we're going to move on to exercise 11, where we do the same thing, but the operator is now the second derivative. This works out nice because we can just take the derivative of the derivatives that we just took. So for the first function, e to the ikx, we had the first derivative equal I times k times e to the ikx. So now we can just take the derivative of this, and we get, the process is the same, just bring down what's in front, ik squared e to the ikx, which I squared is -1, so we can just write negative k squared e to the ikx. So here, we get the wave function back, and we get a constant. So this function is an eigenfunction of the second derivative operator. So I'll write yes, eigenvalue is minus k squared. For the next one, which was cosine k of x, the first derivative was minus k sine kx. I'm going to move down here. So the derivative now of the first derivative equals minus k squared cosine k of x. So we check, we get the same psi, and we get a constant. So even though this function wasn't an eigenfunction for the first derivative, it is for the second derivative because we get the wave function back with a constant. So here the eigenvalue is minus k squared again. For c, which was kx, the first derivative was just k. So taking the derivative of k with respect to x gives us 0. So no function, no wave function, even though we get a constant of 0, this is not an eigenfunction of this operator. And then finally, we have e to the minus ax squared, where the first derivative was minus 2ax e to the minus ax squared. So now we get to take the derivative of this and we get to use product rule. Okay, so let's write this over here. d dx of minus 2ax e to the minus ax squared. And we can factor out these constants because they're not going to be needed anyway. I'll bring that down. Oh, I'm going to need some more room. Okay, that's better. Okay, so we have minus 2a d dx x e to the minus ax squared. And we need product rule, which is 1d2 times 2d1. That's just how I learned it. Everybody has their ways. So to me, that's minus 2a 1 d2 or plus, sorry, not times, plus e to the minus ax squared, which is 2 d1. Simplify. We get minus 2a, negative 2a to the x squared, e to the minus ax squared, plus e to the minus ax squared. Distributing, we get 4a squared x squared, e to the minus ax squared, minus 2a e to the minus ax squared, which finally, condensing, factoring out these exponential values, we get 4a squared x squared minus 2a e to the minus ax squared. So here, psi is back. Similarly, because of the presence of this variable, we can't say that it's a constant after all that work. So we conclude, no, this function is not an eigenfunction of the operator d dx squared.